All right, so this problem reads, a fairground ride spins its occupants inside a flying saucer-shaped container. If the horizontal circular path the riders follow has an 8-meter radius, how many revolutions per minute will the riders be subjected to a centripetal acceleration whose magnitude is 1.5 times that due to gravity? All right, so we want to know what is the revolutions per minute that those occupants are feeling. If they're feeling a centripetal acceleration of 1.5 times g. So let's first look at what that centripetal acceleration, remember. Our centripetal acceleration, we're told it's 1.5 times 9.8. So the centripetal acceleration that these occupants are feeling is 14.7 meters per second squared. So pretty high. We know that the centripetal acceleration is equal to the tangential velocity squared over the radius. Now we want to know revolutions per minute, so that means we want something to do with the angular speed. Well, if we remember that the linear velocity is equal to the radius times the angular velocity, I can use that in this relationship for centripetal acceleration to put it in terms of angular speed. And we find that the centripetal acceleration is equal to omega squared times the radius. All right, so 14.7 is equal to omega squared times the radius of 8. So I determine then that omega is equal to 1.35 radians per second. So omega is 1.35 radians per second. Now we want to determine revolutions per second. So our 1.35 radians per second times, we know that there are 2 pi radians in 1 revolution. And of course, there are 60 seconds in 1 minute. And we find the revolutions per minute to be 12.9 revolutions per minute. All right, so recognizing what centripetal acceleration is, how it's related to our angular velocity, which is what we're interested in, and finding our angular velocity, which is in radians per second, and then determining our revolutions per minute. All right, good job.